Hello, everyone, and welcome to lecture number 10 of our training course on advanced earthquake and tsunami hazards. We are excited to be able to give you these lectures. So let's get started right away and have a look at what we have in store for you on lecture number 10. So as you know, this is part of the 2020 Advanced Earthquake and Tsunami Hazards Training course, prepared by USGS in cooperation with the BMKG and funded by USAID. We're glad that you are here. And today I'll summarize what we know about earthquake and tsunami hazards in this large and very interesting region. So the study area is very big and involves complicated tectonics in eastern Indonesia that you've already heard about from previous speakers, and meanwhile active subduction beneath Java Sea and Sunda in the area to the west. So basically we can divide our study area into continental region, which has a thickness of about 40 kilometers. And there we have stable subduction taking place. An oceanic regime ranging from the South China Sea down to the Banda Sea. And there we find complicated geometry of all the subduction systems. So the reason these are important to keep in mind is the great difference in the physical properties between oceanic and continental crust. So the oceanic crust is about 12 kilometers thick, has 4 to 5 kilometers of water overlying it, and about 7 kilometers only of the crystalline crustal material. In contrast, continents are about 40 kilometers thick and have 3 distinct layers. So what we find is that when subduction occurs beneath the continent versus ocean, the evolution is quite different. Now we can trace this evolution of subduction systems and of the movement of plates by looking at the magnetic anomalies on the seafloor. So in image number A in the back, you can see that the beginning of spreading produces a pale orange stripe. And as the ocean floor continues to spread, shown in panel B in the middle, this pale orange has moved to the left and right, and a new series of new amount of oceanic crust is formed at the mid-ocean ridge. And if the magnetic field of the Earth reverses, you begin to get the magnetic reversal pattern. Therefore, looking for these magnetic anomalies from marine surveys, allows us to reconstruct the history of the sea floor. So back at 160 million years before present, we had the big Mesotethyan Ocean. So the Tethys is the name given to the big ocean basin that separated southern Asia from the continental mass of Gondwana, including Australia and India. And there was subduction occurring at various boundaries in South Asia. At 110 million years before present, India rifts away from Africa and Australia and begins its journey to the north. And there's the initiation of a pair of subduction zones south of the Asian continental mass. You can see the beginning too of the extension of the Banda embayment in northern Australia. At 70 million years, India is now approaching southern Asia, and subduction continues, but we don't have any existence yet of the landmass the lands that will form eastern Indonesia. Finally, India begins to collide with South Asia at 45 million years before present. And we have a pair of subduction zones that begin to form in eastern Indonesia, creating the Celebes Sea, the Philippine Sea, and the Proto-South China Sea. Let's take a closer look at this situation at 45 million years before present, using the map of Robert Hall, published in 2012. And here you can see a pair of subduction zones with the South China Sea and Pacific Plate subducting to the south, and the Indian-Australian Plate subducting to the north. By 30 million years, we have a rearrangement of geometry and the beginning of the formation of the Philippines. Northern Sulawesi is already formed, some of the other islands, and there is a curvature taking place in the subduction system of eastern Indonesia. Now, in western Indonesia, you have ongoing subduction beneath Java and Sumatra. At 15 million years, India has moved closer to Asia, beginning the formation of the Himalayas and the Tibetan Plateau, and we begin to get close to the geometry, the final geometry of eastern Indonesia, with again the Celebes Sea, the Philippine Sea growing in size, the opening of the South China Sea, and strike-slip faulting in the northern part of Papua New Guinea. Let's take a closer look at what this looks like at 15 million years. Again, we'll go through some of the key features. South China Sea is opening, subduction is occurring to the east. The Philippine Sea Plate has grown in size, so has the Celebes Sea, and the Malacca Sea is now in its infancy, and there is strike-slip faulting north of New Guinea. At 5 million years, we're getting nearly to the present geometry, and we have the great complexity in the east. Ocean continent subduction continues in western Indonesia, but we now have the formation of the Philippine Islands through the active volcanism, and strike-slip faulting occurring on the Sorong Fault in eastern Indonesia. So the present day geometry, again, familiar to you, here is the Sorong Fault located here, and the fault that, the strike-slip fault that cuts through Sulawesi, Celebes Sea, the Philippine Sea Plate to the east, and the geometry shown here with curving subduction zones wrapping around the Banda Sea, and the simpler ongoing subduction of the Indian-Australian oceanic crust beneath Java and Sumatra. So what do we learn from this comparison of eastern versus western Indonesia? Well, ocean continent subduction is steady, uniform, and long-lasting. That's the subduction that we see beneath the Sunda Plate. Ocean subduction is complex, rapidly evolving, and short-lived. You see these subduction zones are constantly curving and bending and rearranging their geometry. So now I offer you the C.V. Raman Prize to anyone from BMKG who can give a complete mathematical, physical, and geophysical explanation for why ocean subduction is more complex and shorter lived than ocean continent subduction. So here's your first challenge. If we look at the seismicity, here's 5 years of seismicity. We can see that the plate boundaries are very clearly outlined by the seismicity. Blue is the shallow earthquakes, dark red are the deepest earthquakes going down to almost 700 kilometers. And these earthquakes align themselves on the active subduction zones and tell us where active tectonics is taking place. we can look at 20 years of data, and this really fills in the picture. It's quite stable with the region of Malaysia and Borneo, aseismic, as compared to the very active seismicity at all the subduction zones. The 2004 Great Sumatra earthquake is shown here, as well as the very strong offshore earthquake from 2012 on the oceanic crust. Deep earthquakes don't occur everywhere. There are more blue earthquakes than red, and this is an interesting pattern, that they are abundant under the Banda Sea, less abundant under Java, and pretty rare under Sumatra. In contrast, we have many of these earthquakes beneath the Celebes Sea. So the intermediate and deep events are shown here only. You saw this previously in the presentation from Sean Hutchings, and you can see that they follow the subduction zones, and the pattern of truly deep earthquakes shows a very interesting decrease going from the Banda Sea over to Sumatra. Abundant deep earthquakes under the southern Philippines and the Celebes Sea. So if we look at these cross sections, cross-section D and E, you can see the pattern that is formed. For cross-section D, shown here on eastern Java, the Benioff zone, the pattern of seismicity is very clear to a depth of 200 kilometers. Then there's a seismic gap and deep earthquakes down at around 500 to 600. So this gap can be due to either an absence of the plate or an absence of stress in the plate. If we look at profile E prime, between Sumatra and Java, we see a different pattern. Again, shallow earthquakes make their way down to about 200 kilometers, and we have the gap, but we have, in this case, very few, in this case, only one really deep earthquake at a depth of 650 kilometers. So we need to have new and modern and better seismic tomography models to tell us for sure whether there is a plate here. It has been previously suggested by Hall and Schbachmann that perhaps there is a hole in the subducting plate at this location. We need to confirm that. Well, let's look at the seismicity in the southern Philippines. We have profiles A and B going through this very active nest of seismic activity. So Celebes Sea seismicity, you can see a concentration to the west and then a second concentration to the east. And this will show up as being two separate plates with deep earthquakes off to the west. So here we have the Philippine Sea slab subducting down to a depth of only about 200 kilometers, and the Sang-i slab going down to a depth of great depth of 650, with many, many earthquakes at great depth. Here we have a seismic gap, but a huge number of earthquakes at greater depth. Very different, for example, than the Sumatra example. So if we look at the Celebes Sea cross-section B now, this is the southern cross-section. We're going to look at section D. Then you see another surprise. In this case, it's continuous seismicity all the way down to 660 kilometers on this well-defined slab. Now we can look at this also from seismic tomography. So let's look at the P-wave tomography of Fan and Zhao 2019. And they can follow the subducting plate by looking at the P-wave velocity. This shows it's a positive velocity anomaly with a magnitude of about 1 or 1.5%. The earthquakes are in white, and so the earthquakes in the high velocity blue region outline the subducting plate going down to 660 and also the Philippine plate. This is for cross-section G, and we can look at these other cross-sections D, E, and F. They are shown here, D, E, F, and G, and they are located here in the southern Philippines, D, E, F, and G. And you can see the orientation of the subducting slab with evidence that perhaps the slab in some places is broken off and falling into the mantle. So you can see evidence for non-continuous subduction, or maybe it only began a short time ago and the plate hasn't gone down very far. Banda C seismicity is very active with many deep events. Now we're looking at this region here that goes through Timor, C prime, and there you can see the Banda plate. This is the northwest is on this angle, and the earthquakes go all the way down to 660 kilometers and then go through a bend. Big cluster of earthquakes at a depth of about 550. How about the focal mechanisms? Well, let's remind you of the nature of these focal mechanisms. So if you have a strike-slip fault, like shown here, then you have compression in this quadrant, tension in the other, and likewise compression and tension. For a thrust fault, you get this kind of pattern with the compression axis centered in the middle of the focal mechanism. And for normal faulting, you get just about the opposite. Here's a fault, a normal fault with the hanging wall sliding downward, and this is indicated by the tension moving downward in this case. So normal faults, we'll see that there is good evidence for normal faulting in the deep earthquakes, but also in some cases some thrusting. So let's take a look. Here's a normal faulting event beneath Sumatra from the 7.3 in 2004, strong normal faulting. Here, thrust faulting at a depth of 220 for the earthquake in 2007 beneath Java. And here we again get normal faulting with the strike-slip component of it beneath the Banda C. So quite a diversity in the focal mechanisms of the earthquakes at depths between 280 and about 600 kilometers. So these are indicating then intraslab deformation. And at the trench, we have the very low angle thrust faulting on the megathrust, but within the plate, we get more complicated solutions, sometimes normal faulting and sometimes thrust faulting. You've seen from the previous lecture the pattern of earthquakes versus depth. Here, depth goes to 700 kilometers. The deepest earthquake is about 670 kilometers. And there's a steady drop in the number of earthquakes per year until we reach the mantle transition zone, the 410 boundary. Then it decreases again. And then there's a bit of a peak in the middle of the transition zone and an abrupt fall off. That's a very interesting pattern. In the case of Northwest Sumatra, the earthquakes only go down to 200 kilometers. But for the other regions, they show this very clear pattern of decrease followed by an increase at a depth of about 400, and again, another increase at about 600 kilometers. So here's the Chandra Sanka Prize. I offer the opportunity for anyone listening to try to explain this kind of pattern, to look at the deep earthquakes in Indonesia and explain this with scientific evidence. What is the cause of this pattern of decreasing seismic activity followed by the increase? So that's a challenge for you to solve this problem. So, as Sean previously said, the complex high seismicity is concentrated at plate boundaries. The depth distributions trace the Wadati-Benioff zones of subducting slabs. Deep intraslab events show different source mechanisms, which are depending on the stress at the different locations. And as you know, because these earthquakes are very far from the Earth's surface, intermediate and deep events pose relatively low seismic hazards. But what about active source seismic, for example, seismic reflection methods for studying the structure of Indonesia? Here is a diagram showing the shot points and many recorders and the ray paths for a seismic reflection survey. These surveys have been carried out by the German group from the German Geomarine Institute in Kiel. Many profiles carried here, they're numbered up to 8. This is from a report by Lucien et al., 2011. And we'll look at an example from line 1. So here we see to the south, this is the oceanic crust at a depth of about 3.5 kilometers. And the oceanic crust can be traced beneath the forearc offshore of Java. This is the top of the oceanic crust. And then the trench is located here, water depth of 6 kilometers. This is the overlying accretionary prism. Now this is blown up, this dashed box here is blown up, so you can see how clearly the geometry is outlined, and there are faults within the forearc region as well. So this is a really spectacular example of tracing the oceanic crust as it descends beneath the forearc. If we look at a bigger picture in the Lombok forearc basin, you can see that the oceanic crust descends here and eventually plunges down into the mantle, as we saw from the seismology, the seismicity. And there are faults that come off of the megathrust boundary, and we call these splay faults. Well, these splay faults are very dangerous because they have the potential to create very big tsunamis. We can also study this geometry and velocity structure of the oceanic lithosphere descending beneath the forearc using active source seismic refraction seismology. So this is where the airgun sources are penetrating through the different layers and are recorded to long distances. This is a very good measurement of the velocity structure. It's not the same as the seismic reflection. Reflection is more like a oil company exploration with the vertical incidence. So we'll look at one example of a cross-section taken from Western Java. So this is the structure of the Java convergent margin based on the refraction surveys. Here's the trench, as we know, the subducting oceanic crust, the accreted sediments of the forearc prism, and the forearc basin. Another picture looking generally similar. Here you can see the high velocity forearc crust. That's the crust that the sediments are being deposited on, and the subducting plate that can be traced to a depth of about 20 kilometers in this case. So this is a very successful effort to image the fine structure of the subducting oceanic lithosphere and the forearc basin. So the megathrust boundary is here and here. So what are the conclusions from studies of the Java convergent margin using active sources? Well, first of all, tsunamigenic earthquakes are very common. We know that from the history, but splay faults are everywhere, and splay faults are very dangerous because they can move the ground vertically and cause a very large tsunami. Also, the splay faults are closer to the land, so the tsunami will come more quickly. And they found that tsunamigenic landslides are abundant because of the steep slopes. So let's look again at those splay fault. I want to emphasize this point. Here's the trench. If you have an earthquake and it gives deformation of the ocean floor and creates a tsunami here, this is from 50 to 150, this is 100 kilometers to this point, whereas the splay fault is half that distance. It's about 50 kilometers. So the time of the travel time of the tsunami wave will be much less from the splay fault. Okay, so let's move on then to Palu and talk about the earthquake that occurred there in 2018. This is a region in eastern Indonesia that has had many tsunamigenic earthquakes in the last 20 years. In this particular case, it occurred on a strike-slip fault with a left lateral motion. The Palu earthquake epicenter is located 80 kilometers north of the city on a fault that was not well identified previously. The main fault trace was believed to have been out here, but the rupture broke the ground and it can be traced on foot very accurately. And the earthquake, the fault then passed through the city of Palu on the west side of the city. Tsunami waves arrived within minutes after the main shock. Most of the fault was on land, but it did pass beneath the Palu Bay. And the maximum inundation was 468 meters with run-up heights of 2 to 9 and greater heights for the tsunami wave. The run-up height refers to the maximum height of the incoming wave where the inundation finally stops. So you've seen these pictures before, Talis Beach, Mamboro Beach, with devastation caused by waves which are 2, 3, and 4 meters in height and have run-ups that are even higher. So now I offer the listeners an opportunity to use their creativity and their scientific knowledge and win the James Hutton Prize, which would be to explain how does a strike-slip fault with an epicenter on land create a devastating tsunami with great run-up heights of up to 9 meters. So this is your challenge. You need to think about this and form your own hypotheses. Of course, one hypothesis is that there is some bathymetry beneath the Palu Bay, and when the strike-slip fault moves, it moves the water because of the particular geometry beneath the water surface. And another idea was that this triggers landslides. So here's layer 2, this orange layer that slumps, and when the subsurface moves, it generates a tsunami wave. But the challenge for you would be to try to put together a comprehensive model for tsunami generation based on your BMKG data. Liquefaction was very severe, as you heard. Here is the map of the Palu region with 3 places that suffered serious liquefaction. And we'll look at the Balarora liquefaction site. Here's Balarora before. The BMKG office is located over here. And as you know from your media and reading and scientific work, the ground liquefied and began to flow, carrying houses with it and burying, unfortunately, many people beneath the churning sediments of the liquefaction. Terrible event. That's why in this course, we have added a lot of material about landsliding and liquefaction. These lectures will be given by Jessica Reed and Marcella Cilia. So here's the location of the Balarora site. And here's the flow. You can see that bare ground is all that you can see now, whereas before there were houses. The houses are buried beneath this, and deformation occurred down further to the east. So the 2018 Palu-Sulawesi left lateral strike slip fault caused a huge tsunami and major liquefaction. Tsunamis have many sources, as you know, and this is we've been emphasizing. These are the locations for tsunamis involving volcanoes. So the volcano erupts, and if it's near or under the water, it causes a displacement and causes very strong tsunami. So compared to earthquake-generated tsunamis, volcanically generated tsunamis are fewer, but they can be very dangerous and very strong. And here are the locations here. Krakatau, of course, 1883 was a huge tsunami, created a huge tsunami. Earthquake sources of tsunamis, more than 100 in Indonesia. This is information from compiled by ESRI, the Earth Science Research Institute. And you have your own BMKG catalog, which is probably more complete. But you can see the distribution of earthquake-generated tsunamis is very wide. Sumatra 2004, of course, took place in Western Sumatra. Tsunamis involving landslides. Well, not as many as caused by earthquakes, but still significant, including the Palu event and about 8 or 10 other events. So this is landslide-induced tsunamis. Lambata is a good example from 1979. And mixed causes is very common. You have an earthquake, it generates a landslide, or a volcano that generates a strong landslide. And these mixed cause cases occur throughout Indonesia. Palu is a good example of a tsunami that was unexpected because it was a strike slip fault, but it caused a tsunami by a mechanism related to either landsliding or the geometry of the seafloor or coastal collapse. Anuk Krakatau, of course, you know about. It's a active volcano, and it was a flank collapse that caused the tsunami at that place, claiming more than 400 lives. And then there are some cases where tsunami occurs and we don't have a clear understanding of what caused it. It can be that there is no seismic evidence, it's late at night and the wave comes in with an unclear origin. So you saw this summary diagram before, which is the distribution of the tsunami causes, 81% being due to earthquake and the other 19% having these other causes. So now I can summarize by saying that tsunami sources are ubiquitous. They are present everywhere in the world, South America, Caribbean, in the Mediterranean, and of course in the Western Pacific. And we still have a long way to go to understand all of the mechanics that generate these strong tsunamis. So don't forget, I mentioned there are 3 prizes being offered to explain: the Raman Prize to explain oceanic subduction complexity, the Chandra Sankar Prize to explain that diagram of earthquakes per year versus depth in the mantle, and the Hutton Prize to explain the origin of tsunamis for strike slip faulting. I hope someone will one person or more will take up the challenge for each of these 3 challenges. Thank you for your attention, and we will take questions.